today we will do some problems on the same solid liquid separation, problems related to filtration, problem related to centrifugal separation as well as centrifugal filtration. Let us recall the time required to filter on a flat bed of certain solids. So if you recall this is the equation which you looked at, and the equation was obtained using Darcy's law. So the equation says that time required to filter is a function of many parameters: the viscosity of the medium, the volume that needs to be filtered, and it is inversely proportional to the area and the pressure drop. So if the pressure drop is very high, then time required will be less, and if the area is very high, time required will be less. Now similarly you also have an equation for centrifugal filter. The centrifugal filter, I think I explained in the previous classes, can be used to filter solid using a centrifuge. So this filter contains a basket, a porous basket, and the cake is formed along the periphery of the cylindrical portion of the centrifuge. The liquid flows through the solid bed that is formed and escapes out. So here the bed is in a cylindrical form, whereas in a flat filter the solid that gets deposited is in a flat form. So that is the main difference on the centrifugal filter as well as on the flat bed filter actually. So the time required to filter it depends upon several parameters here, because it is a centrifuge. We have the angular velocity of the centrifuge, we have the several radii terms coming into the picture. R0 is the radius of the centrifuge, RC is the radius up to the top of the solid bed, R1 is the radius of the liquid level, and of course you have terms like L, which is the height of the centrifuge or length of the centrifuge, and also you have the density terms coming into the picture here. Now let us consider a problem which involves both the flat bed centrifuge as well as this flat bed filter as well as the centrifuge. Suppose I am doing an experiment in my lab using a flat filter, area is 10 centimeter square, and I am filtering 500 ml of a slurry containing 0.02 grams per cc of cell debris, and I am able to achieve it in 30 minutes using a pressure of 1 bar. Now the solids in the cake has a density of 1.1 gram solid per cc, and the liquid has the properties of water. Now you collect data in the lab generally using a simple filter, flat filter, like you use a Buchner funnel like, and then put in a filter cloth or a filter paper, and then you achieve this filtration. Now you want to scale it up to a large scale, so you do not like to do the same operation, you would like to use a centrifuge, that means a centrifugal basket filter. Now the dimensions of this centrifuge is, it has got a 50 centimeter radius, okay, that is R0, and it has got 45 centimeter height, okay, that is the length. It rotates at 500 revolutions per minute. The liquid level is 45.5 centimeter, that is this portion. Now how much time it will take to filter 2000 liters of slurry? So you understand, I do certain experiments in my lab using a very simple setup, a flat filter, and then I want to scale it up to a large scale operation where I want to filter 2000 liters using a centrifuge. Some dimensions are given and you are asked to calculate what should be the time taken to filter 2000 liters of this slurry if you use this particular type of centrifuge. you assume the properties of the solid to be same when you move from the lab scale right up to the manufacturing scale, that is important. So what do? You calculate the properties of the cake from the lab scale data and then use that and put it inside the equation for the centrifugal filter and calculate the time required. Now many data are given for the lab scale flat filter. Now if you recall again, this is the equation for the flat filter, the time in terms of the volume that needs to be filtered, the viscosity, the rho naught, the area of the filter setup and the delta P. So it says 30 minutes, so we are converting that into seconds, and then volume that needs to be filtered is 500 cc, so I have put in here. Now these two are unknown, so this is the unknown here, and rho naught is given as 0.02. Now area is given as if you recall properly, it is a 10 centimeter square flat filter area, so you put in 10 centimeter square, and then the delta P is 1 atmosphere, so you are converting that properly here. So you have the left hand side, you have the right hand side, the only unknown is mu sigma c. This determines the properties of the solid and the liquid, so we can calculate from this equation this whole thing. Okay. Now we need to calculate in the centrifugal filter the thickness of the cake. So how do? You can do a mass balance from this particular data set. The data that is given is you want to filter 2000 liters of slurry and the solids in the cake has a density of 1.1 gram solid per cc, correct, and then you know the overall radius of the centrifugal filter. So we can do a mass balance and from there we can calculate what will be the thickness of the cake, that means we can calculate what will be the RC, understand. So you have V into rho naught, V is the volume that needs to be filtered in liters, so we can convert that into cc, and then rho naught is the density, so that gives the amount of solid material that needs to be filtered, that is on the left hand side. Now on the right hand side we can do the amount of solids present or the solids that is going to get accumulated in the centrifuge. This is like pi L is the height of your centrifuge, R naught square minus RC square, that gives you the area of the cake, cylindrical cake that forms in the centrifuge, understand. So pi into height into area of the cylindrical cake gives you the volume of the cake that forms in the centrifuge, and you are multiplying by the density rho c, which is also given. If you see, the solids in the cake has a density of 1.1 gram per cc, so that is given, so that is what we are going to use here, that is the 1.1 cc here. So what you are doing is you are balancing the amount of solids present in the slurry with the amount of solids or amount of cake that deposits on the walls of the centrifuge. By balancing these two terms, for example this relates to the amount of solids present in the slurry and the right hand side gives you the amount of cake that deposits on the walls of the centrifuge. By balancing these two terms we can calculate RC, that is the level of the cake, whereas R naught is the radius of the centrifuge, which is given as 50. Okay. So we put volume as 2000 into 1000, so you are converting that into cc, and then the density is given here, grams per cc, then you have pi here, and then length of the centrifuge is 45 centimeters, then R naught square minus RC square. R naught is the radius of the centrifuge which is given 50 centimeter. So and RC is what you do not know, agreed, and then density is 1.1. So now we know all the terms except RC. So RC is calculated as 47.36. So you see the thickness of the cylindrical cake that is formed during the centrifugal operation will be 50 minus 47.36, do you understand. So that will be around 2.74 centimeter. So 2.74 centimeter thick cylindrical cake is formed with V rho naught quantity of the solids present in your slurry. So this equation is a mass balance of the amount of solids present in the slurry with the amount of cake that gets deposited in the centrifuge when you process this much amount of slurry. So by doing this balance we are calculating the level of the cake, okay, that is what is RC. Okay. Why do you need this RC? We need this to calculate the time required to process 2000 liters of the slurry in a basket centrifugal filter, because that is not given in the problem, only the radius of the centrifuge basket is given actually. So to calculate that we use this particular mass balance equation. Okay. So we go back to the equation which tells you how much time will be required to filter V liters of the slurry in a centrifuge of radius R0 and length L. So we just put in all the data here, and remember that RC is what we calculated from the mass balance, that is 47.36 centimeter. R0 is the radius of the centrifuge, that is 50. Okay. So by doing all this what do we get? We get the time required to filter so many liters of the slurry as 7.75 minutes. So this particular problem is a combination of both flat bed filter as well as the centrifugal basket filter. So you carry out some experiments in the lab using the flat bed filter, and those data will be used to estimate the resistance offered by the cake as well as the viscosity of the fluid, and then you take that data and put it inside the equation for the centrifugal filter, and from there you calculate the time required to perform this particular operation, it is the centrifugal operation and centrifugal filter. And that is what is normally done if you are translating data from the lab to the large scale manufacturing plant. So in the lab you might not do the filtration operation using a centrifuge, you generally use a simple flat filter setup, and then you apply certain pressure, you know the area of the filter setup, and then you estimate what is the time that takes to filter certain amount of slurry, and then using that data you estimate the resistance offered by the cake, and then use that to calculate what is the time required to perform the filtration using a centrifuge. So these two equations are very useful to do this type of scale up. One important point which you need to remember is that when I use a flat filter, the cake that is formed is flat, whereas when I use a centrifugal filter to filter the solids, then the cake that is formed is cylindrical. Okay. So there is a difference between the cakes that is formed. If I use a simple flat filter, the cake will be flat, so the equation will be like this, whereas when I am using a cylindrical basket centrifuge, then the cake also is going to be a cylindrical, and the cake will be like R0 minus RC thickness, but it will be in the form of a cylindrical cake. So the equation for the time will be like this. So you see these two equations they look similar, but the main difference between these two equations is that the cake that is formed in a flat filter will be flat, whereas the cake that is formed in a centrifugal filter will be of centrifugal shape. Okay, let us look at another problem where you have mixtures of solids that needs to be separated. This is very common actually, you know, after a fermentation broth we may have many different solids that needs to be separated. So each solid may have certain size, each solid may offer different resistance during the filtration operation. Now you consider a broth which contains bacterial and fungal cells. Now you want to know how long it will take to filter 1000 liters of a broth in a filter of area 5 meter square, and we assume that the filter medium does not offer any resistance and you are applying 1 bar pressure. Now the bacterial cells have certain property, like the size is given here 7 into 10 power minus 4 centimeter, and the resistance offered by it is given here 1.3 into 10 power 9, whereas the fungal size is different and resistance offered is also different, and we will assume 50-50 ratio of the bacterial and fungal. Now the problem states that we can consider average properties, that means we can take the ratios to be directly proportional to each other. Okay. So that means if you want to calculate the mu sigma c rho naught for this combined system, we can assume an average of 1.3 into 10 power 9 and 2.5 into 10 power 9. So that is what it says, we can assume average properties. So the problem becomes very simple. We know the amount of slurry that needs to be filtered, okay. Then we take an average of this and use it here. We know the area of the filtration setup, we know the delta P, that is 1 bar. So all you need to do is introduce all those terms here and calculate T. So it is very simple, straightforward. So you get 6.3 minutes. So it takes 6.3 minutes to filter a mixture of bacterial and fungal of equal proportions, but they have different resistivity. One important point you need to remember is you need to convert the 1 bar pressure that is applied during the filtration to Newton per meter square. So that is very important, that comes here actually. So units is very important when you do problems of this nature. You see we have looked at combinations of units, centimeter square, meter, Newton per meter square, bar, atmosphere pressure, liter, cc. So many different units appear in all our problems. So please keep note of this and make appropriate conversions, otherwise you will end up with wrong answer, do not forget that, make appropriate conversions. Okay, so this particular problem we have mixtures of 2 solids which needs to be separated, and each solid has a different resistance offering, and the time is found to be 6.3 minutes. Now let us look at the problem slightly in a different fashion. Now imagine a slurry with 2 types of particles. You have 2 types of particles, one of 0.1 mm and the other is of 0.05 mm. Now suppose I consider only one filtration setup and I have very fine pores so that it is able to capture both 0.1 and 0.05. Okay, so the pores here are very fine. Now consider another filtration setup, 2 filters are there. The first one has a very coarse holes, so it will capture only 0.1 mm, 0.05 will pass through. Okay. Now this 0.05 is captured in the second filter, that means the holes are very fine. So you have two systems, one system where the holes are very fine, so both 0.1 mm and 0.05 mm is captured. In the other place you have two filtration units, here the holes are very coarse, so only 0.1 mm is captured, 0.05 escapes, which is captured in the second filter. Now two systems are there, now will the filtration be faster in this or the filtration will be faster in this? So here we have only one filtration setup and you are capturing both 0.1 mm and 0.05 mm, whereas here we have a coarse filter which captures 0.1 mm and then a fine filter which captures the remaining 0.05 mm. So will the filtration be faster in here or the filtration be faster here? Both will be the same, there will not be any difference. Why? Because if you look at the Darcy's law equation, the size of the particles are not coming at all into the term, right. Please remember the Darcy's law equation, the terms in the equation is the amount of slurry that needs to be filtered, the viscosity of the fluid, the resistivity offered by the solids, area of the filtration unit, density of the slurry, pressure applied, but the particle size is not coming into the picture. So obviously filtration does not depend on the particle size according to the equation, but actually in reality it will have so many effects. If you have very fine particle, the particles may go and block the holes, so after some time the filtration may totally stop. If you have a very coarse particle and fine particle, the resistivity may change, that it means the resistance offered by the particles for the flow of the fluid may change. That is why we sometimes add some filter aids. Sometimes if the particle is very fine, it may even compact and it will offer certain pressure during filtration. So in reality so many things can happen because of fine particle and vis-a-vis the coarse particle, but if you look at the Darcy's equation there is no mention about particle size, so filtration does not depend on the particle size at all. Another important parameter, if you remember, you might have studied in fluid flow through packed beds, the pressure drop across packed beds are definitely related to the particle size. If the particles are very fine, pressure drop increases, if the particles are very coarse, the pressure drop is less. You must have heard about equations like Ergun's equation and so on, which measures pressure drop across a packed bed. So there a particle size plays a very important role. So but in Darcy's law equation we do not have specifically term for particle size, but in reality particle size comes in various places, so you should keep that point in mind. Okay, let us look at something related to settling. So you would like to perform certain settling operation, so we have some immobilized animal cells of 150 mm, okay, so sorry it should read it as 150 micron and density of 1.04 grams per cc, and you would like to separate it from the liquid medium in a settling tank. So the slurry is taken in a cylindrical vessel of a diameter 10 centimeter and height 70 centimeter, okay. So the diameter is 10 centimeter, height is 70 centimeter. Estimate the settling time assuming the particles quickly reach the terminal settling velocity. the liquid has a density of 1 gram per cc and viscosity of 1.1 centipoise. So we have certain particles of 150 micron and a density of 1.04. Now let us look at a problem related to settling. Now consider immobilized animal cell, particle size is 150 micron and it has got a density of 1.04 grams per cc. Now you would like to separate this particular animal cells from a liquid medium in a settling tank. So we would like the solids to settle down to the bottom, so that you will have a clear liquid at the top and the solids right at the bottom. Okay. So we are doing this in a cylindrical tank, so the diameter is 10 centimeter, the height is 70 centimeter. Now I would like to know how long I should allow it so that the solids will all settle down. The assumption here is the solids quickly reach the terminal settling velocity, and then the liquid has a density of 1 grams per cc and a viscosity of 1.1 centipoise. Now if you remember the Stokes law, which we taught in the previous classes, the velocity, that means the terminal settling velocity, arises because of the balancing of the drag force and the buoyancy and the acceleration due to gravity. This velocity depends upon the diameter of the particle, difference in the density between the solid and the liquid, and the viscosity of the fluid, which comes in the denominator. So I hope you remember this equation. So the diameter of the particle is given here, rho s, rho l are given here, viscosity is given here. So we can calculate the terminal settling velocity, right. Once we calculate the terminal settling velocity, I know the height of the tank. So from there I can calculate how long it will take particle from the top coming down at the bottom, okay, because that is what you want to calculate. You want to calculate the settling time. So we introduce all the terms in our Stokes equation. So we end up with a terminal settling velocity of 0.0445 centimeter per second. So the settling time will be height divided by velocity, okay. So the height is 70 centimeter, that is the height of the tank, and if you divide by the velocity you get 1571 seconds, that is about 26 minutes. That means it takes 26 minutes for a solid which is at the top of the liquid level to reach the bottom of the tank of height 70 centimeters. Now the Stokes law again, if you remember, recall that it is valid only when Reynolds number is very low, that means Reynolds number less than 1. So we need to confirm or check whether the Reynolds number is really low, otherwise Stokes law is not valid. Why is it so? If you remember, Reynolds number is a function of many parameters, right, diameter of the particle, particle velocity, and the physical properties of the liquid. Now if the velocity is very high, it may create a turbulence, then the Stokes law is not valid, okay. So we again have the particle size, we have the particle velocity here, we know the liquid density, we know the liquid viscosity. So we introduce all the terms and we find that the Reynolds number is very small, much less than 1. So it is okay for us to use this particular equation, otherwise it is not correct. So Stokes law depends upon dilute solutions, that means the solids that are settling down is not disturbing or impeding the solids that are present. So that may, one solid may affect the movement of other solid either through collision or creating eddies or creating turbulence, then we cannot use the assumptions of Stokes law. that means if the concentration is very high we cannot use the Stokes law. If the velocities are very high in the form of turbulence, then again Stokes law is not very valid. What happens if the particles are not very spherical? We can still use Stokes law, we will use something called the characteristic diameter of the particle. How do you calculate characteristic diameter of the particle? All we can do is get the volume of the particle divided by the surface area of the particle. Okay. So, when you do that, from there we can calculate the characteristic diameter of the particle. Now, what is the throughput in the settling tank? How do you calculate throughput? Throughput is the tank volume divided by the batch cycle time. Here the batch cycle time we will assume it as the settling time 26 minutes, and the tank volume is nothing but this is the diameter of the tank. So, it gets pi d square by 4, this is the height of the tank. So, you multiply that gives you the volume divided by 26. So, throughput through the tank is about 210 cc per minute. So, you can process 210 cc per minute of this particular slurry and achieve a separation between the solids and the liquid through settling, and approximately it will take 26 minutes for the solids to settle. But in reality the solids may take slightly more time to reach the terminal settling velocity. So, you may have to keep the slurry inside the cylindrical tank for much longer than 26 minutes to achieve a real complete separation. Let us look at something called scale up. Scale up is a very important part of bioprocess technology or even downstream processing technology, because whatever we do in our lab, the main intention is to emulate or practice in large scale. Large scale could be your pilot plant or your semi technical plant or full manufacturing plant. So, in my lab I may be using 100 cc or 500 cc or 1 liter, but in full manufacturing plant I may be doing the operations in 10,000 liters or 20,000 liters or even 100,000 liters. So, whatever I practice in the lab should be happening in the large scale as well actually. So, when we move from lab to plant, the question always arises, what should be my operating conditions, what should be the size of the large scale vessel. So, if I have a centrifuge of certain dimensions, what should be the dimensions of the centrifuge in the large scale, or if I consider a centrifuge, a large centrifuge, how much difference will be its performance if I compare it with my small scale. So, these questions are always asked by the process engineers or biochemical engineers or scale up chemists. So, there are two different approaches by which we can scale up centrifuges. Let us look at approach 1. I introduced some equations relating to centrifuge long time back, where I said the throughput, that means the quantity of slurry that is flowing through, liters per minute or meter cube per hour, whatever it is, quantity of liquid that is flowing through, is a function of the particle settling velocity and the hardware parameters. That means it is a multiplication of terminal settling velocity and hardware. Hardware means the RPM, the height of the centrifuge, the diameter of the centrifuge, and if you had a disc centrifuge, the number of discs, those are the hardware details. Particle settling velocity involves the physical properties of the solid and the liquid, like the diameter of the solid, viscosity of the fluid, density of the fluid, density of the solid and so on actually. So, if I have certain data on small scale, I can extend it to a similar designed hardware, that means geometrically similar designed hardware using this particular relationship, that means throughput is a function of particle settling velocity into hardware. So, throughput in centrifuge 1 divided by throughput in centrifuge 2 is same, will be equal to the hardware details of centrifuge 1 divided by the hardware details of centrifuge 2, assuming that the particle settling velocity does not change when you move from one scale to another. Okay. So, if you assume that the particle settling velocity does not change, then throughput is directly proportional to hardware. So, I can say Q1 by that is Q1 is the throughput in centrifuge 1 divided by the throughput in centrifuge 2 equal to hardware 1 divided by hardware 2, or I can do some mathematical manipulation and say that the hardware 2 will be equal to hardware 1 multiplied by Q2 by Q1. Okay. So, Q2 by Q1 tells you how much scale up I am going to perform with respect to throughput. So, you multiply the hardware 1 values with this particular ratio of Q2 by Q1. Okay, let us look at a problem. Now, let us recall this hardware parameters for bowl centrifuge as well as disc centrifuge. I have shown this particular set of equations in the previous class. So, for a bowl centrifuge the hardware parameter is like this, okay, where L is the height of the centrifuge or the length of the centrifuge, R is your radius of the ball, this is your revolutions per minute, whereas in the disc centrifuge the equations become slightly more complicated because you have several inclined discs. So, N is the number of discs, and then you have terms like radius of the disc and then angle the discs make with respect to the central axis. But basically if you see these terms relate to the hardware of the centrifuge, disc centrifuge, this term relates to the hardware of the ball centrifuge. Now, the terminal settling velocity of a biomass is given here 1.5 into 10 power minus 5 centimeter per second. It is separated in the lab using a disc centrifuge, and the hardware detail parameters, that means hardware parameters is 2 pi n omega square 3g, you have r naught cube minus r1 cube cot theta. Now, this is equal to 3 10 power 6 centimeter square. So, you have used a lab scale disc centrifuge and you have separated some solids whose terminal settling velocity is given. Now, I want to design a very large scale setup to achieve a throughput of 10,000 liters per second. What should be the hardware details for the large one? Now, the hardware details for the lab centrifuge is given, and the throughput of the large scale is also given, okay, that is 10,000 liter per second, which can be converted into so many cc per second. The terminal settling velocity is also given 1.5 into 10 power minus 5 centimeter per second. So the throughput divided by the terminal settling velocity will give you the hardware details for the large centrifuge. Okay. So you see this is the hardware details for the small centrifuge, this is the hardware details for the large centrifuge. Now the small centrifuge, what is the throughput? You just have to multiply the terminal settling velocity and the hardware, that means 1.5 into 10 power minus 5 multiplied by 3 into 10 power 6. So you get 45 cc per second. So you are scaling up from a 45 cc per second to 10,000 liter per second, that is the scale up. You are using the same structured disc centrifuge. In the small scale the hardware detail, the hardware parameter is 3 into 10 power 6 centimeter square. In the large scale hardware parameter is 0.67 into 10 power 8 meter square, but the terminal settling velocity is the same whether it is a small scale or whether it is the large scale, because the main assumption here is the particle and the fluid properties do not change. Now how do you achieve this particular number for hardware parameter? It can be achieved through so many terms here. It can be achieved through increasing the number of discs, it can be achieved through changing your inclination, that is theta, with respect to central axis, it can be achieved through changing the R0, understand. So that is left to you. You can go to a vendor and look at all the centrifuges available with him, and then you can see which centrifuge has a hardware parameter closer to this, understand. So you may have different combinations of radius, you may have different number of discs, so you can select one of them depending upon which one is closer to this 0.67 into 10 power 8 meter square. So this is a very simple approach by which we can scale up centrifuges moving from the lab to full scale commercial plant. So the main assumption here is the Q, that is the throughput, is equal to the terminal settling velocity multiplied by the hardware parameter. Terminal settling velocity does not change when you scale up from small scale to large scale, because it is a function of the particle properties and the fluid properties. The hardware parameters include the RPM, the radius of the centrifuge, and if it is a disc centrifuge you will also have terms like number of discs and also the inclination the disc make with the central axis. So those are the terms which also appear when compared to the bowl centrifuge and the disc centrifuge. So we are using a tubular bowl centrifuge to recover cell biomass. So if I use 10 liters per minute, I am able to recover 40% of the cells, but then I need to recover 80% of the cells. So what should be the throughput or the flow rate? So it will be directly proportional to the percentage recovery. That means you want to have 80% of cells recovery, that means you would like to improve the efficiency. So obviously you have 40 divided by 80 and 10 is the original flow rate. So the flow rate has to be reduced by a factor of 2. So if I want to improve the efficiency, obviously my throughput goes down. So higher is the efficiency, throughput has to go down. But if I want to have higher efficiency and also higher throughput, then obviously I need to change the hardware parameters. Maybe I will change the RPM or maybe I will change the diameter of the centrifuge and so on. So, those are related to hardware, but if I have the same hardware and tomorrow you are asked by your boss to improve the efficiency of recovery, then the only way you can do is to decrease your throughput. There is no other way at all to do that. Now, one approach we talked about which gives you an idea of how to scale up a centrifugal operation when you move from the lab to a full scale commercial plant. The equation is very simple, it says throughput is equal to terminal settling velocity into hardware parameters. So, that means throughput is directly proportional to hardware parameters, that means throughput in centrifuge 1 divided by throughput in centrifuge 2 will be equal to hardware parameters in centrifuge 1 divided by the hardware parameters in centrifuge 2. So, if I know the details in small scale, I can estimate the details for a large scale. Now, there is another approach by which we could do the scale up, that is called difficulty of separation or the centrifugal conditions. So, difficulty of separation is calculated by looking at the centrifugal force multiplied by time. Centrifugal force is calculated using the angular velocity, the radius of the centrifuge and the time, and of course the g comes there. So, difficulty of separation is given by omega square r t by g, this is called the difficulty of separation. Okay. So, when you move from small scale to large scale, you can keep this omega square r t by g as a constant. For example, for eukaryotic cells this particular term is given like this, for proteins it is given as 9 into 10 power 6, for bacteria 18 into 10 power 6, bacterial cell debris it is 54 into 10 power 6, ribosomes 1100 into 10 power 6. Okay. So, what it means is it is very difficult to separate ribosomes when compared to bacterial cell debris, when compared to bacteria, when compared to protein precipitates or eukaryotic cells. So, obviously it means it is more difficult to separate cell debris than cells itself, and we can scale it up based on the difficulty of separation. That means when I move from a small scale which has certain value of omega r and t, and when I move to larger scale and I want to separate bacterial cell debris, then I can keep the same number 54 into 10 power 6, but it may have different omega, different radius, different time, but the product of omega square r t by g will be the same irrespective of the scale. Whether I do it in a small scale or whether I perform the operation in large scale, I maintain omega square r t by g constant for the particular system, understand. So, in a large scale I will keep omega square r t by g as 54 into 10 power 6 if I am removing cell debris, or if I am doing the same removal of cell debris in my lab, I will still keep omega square r t by g as 54 into 10 power 6 seconds. So, from this particular relation, knowing the r, that means the radius of the centrifuge, and knowing the RPM, I will be able to calculate the time, understand. Or if I know the radius of the centrifuge, if I know the time of the centrifugal operation, I can calculate what will be the omega, because I will assume the difficulty of separation to be constant, and it only depends upon the type of material, it does not depend upon the hardware details, understand. type of material means it could be bacterial, or it could be eukaryotic cells, or it could be protein, or it could be cell debris, or it could be ribosome. So I can estimate this particular term omega square RT by G in my lab. That means I take a small centrifuge, I know the radius of the centrifuge, I know at what RPM it is rotating, and then I separate the solids from the liquid. I find out how long it takes to do that operation, and then I multiply omega square with R and T divided by G, and I will take this term as a constant whether I do it in the lab or whether I do it in the full scale commercial production. So this is the second approach by which we can scale up a centrifuge, and that is based on the difficulty of separation. So the first approach, throughput is equal to the terminal settling velocity into hardware parameters. Second approach is based on constancy of the difficulty of separation. So the difficulty of separation remains constant whether it is in the lab or in the full scale plant, and this term is given by omega square RT divided by G, and we can estimate it in your lab centrifuge, and you find out how long it takes to remove the solids from the liquid or separate the solids from the liquid using a small centrifuge of radius R, which is rotating at a angular velocity omega. Okay, thank you.